Yes, Assalamu alaikum students. I welcome you to one more lecture on differential equations. It is actually the 13th lecture we are delivering on differential equations. We are presently doing the linear differential equations, and in the part of the linear differential equation we have a very important sub topic. It is Bernoulli's differential equation. Before this, we have done what we mean by ordinary linear differential equations. It is the case ordinary one, ordinary linear differential equations of first degree and first order. We have done some applications on this, the rule for solving ordinary differential equations, which are linear differential equations. Now we come to Bernoulli's differential equations. Actually, it is actually Daniel Bernoulli. It is Daniel Bernoulli. It is a great Dutch mathematician. His equation is very important. He has proved that in physics, it is the dynamic pressure plus static pressure is equal to total pressure. In some equations, he has given he is very known mathematician in this kinetic energy, this energy of gas theory. He is famous in this fluid mechanics, hydrodynamics. He is also very famous in astrology. But besides all these fields of physics and mathematics, you will see, if you search the Google in his name, you will see that he has excelled in this medicine also. Very great mathematician, Dutch mathematician. Well, we have to only discuss here his one of the famous differential equation known as Bernoulli's differential equation, ordinary differential equation, this first order and first degree, known as the Bernoulli's differential equation. We have to only learn how to solve it, how to reduce it. Sometimes we give a second name to such differential equations which come under the heading of this Bernoulli's differential equations. Equation is reducible to linear differential equations. These are also known as extended form of the linear differential equation. Let me introduce Okay, we consider here, let us consider a differential equation. We consider a differential equation in fact it is your ordinary differential equation of first order and first degree. dy by dx plus py is q. Now you have here y raised power n. This is my differential equation. You see, we will write here what does this p and q stand for. The same that you did in previous lecture, where p and q are functions of x alone or constants. We write where p and q are either constants, they can be constants, or what? Functions of x alone. And here n, and n is a constant. N is constant. I will mention here it is a constant other than zero or unity. Other than zero or unity. You may check here. If this n is 0 here, then it reduces to the previous form. dy by dx plus py is equal to q. There is no need of giving one more name to this if n is 0. It is the same linear differential equation. Now if n is your unity 1, you can transpose this with this and it coincides with this. It is again solved by, we can simply solve this by variable separable method or by previous method. Therefore this n is different from unity or 0. Well, you see, if we observe here, then how we reduce this differential equation. This is also known as, I will write here, this differential equation is also called extended form of the linear differential equation. Extended form of linear differential equation of ordinary linear differential equation of first degree and first order. Well, you see, if this y raised to power n would not exist here, if you omit y raised power n, then this linear differential equation is of previous form, pure previous form. Then we apply the method of solution what we did previously. But the main thing is here that the existence of y raised power n, which you observe here, we have to somehow remove this. इस y raised power n को हटाना है. अब देखना है कि कौन सा मेथड हम यूज करेंगे इस हटाने के लिए. हमारे पास कैसे प्रोसीजर्स है. क्या हटाने के बाद when we remove it, after removing, do we get the linear differential equation of previous power? In the method of solution we say in method of solution we put y raised power 1 minus n is equal to new variable, say z. Then by this transformation, by this transformation, the differential equation number 1 reduces to standard form of linear differential equation. What is the standard form of linear differential equation? You know, it is our equation which we did in lecture number 12. For that you have to click back to the lecture number 12. We discussed it there. Standard form of dy by dx plus py is equal to q, dx by dy plus px is equal to q, then integrating factor, so on and so forth. Now I will give you this idea. I have written here. We make this transformation y raised power 1 by n is equal to z. Then this differential equation, Bernoulli's differential equation, gets reduced to the original form that we did. I will give you this method of solution. It is very easy. Let us now discuss this method of solution. Method of solution. What is the method of solution? Which method we adopt? We again consider Bernoulli's differential equation, which is dy by dx plus py is qy raised power. I have just told you that it is this y raised power n, which is such that with the help of this we say existence of this y raised power n. It is existing here, it is present on the right side, because this is a function of x we mentioned there, and this is also a function of x, but this y should not exist here. With the presence of this y raised power n, this ceases to be the linear differential equation of standard form. Now, let us we remove this. How we remove it? Remove is simple. We divide by this. Dividing both sides by y raised power n, so that we get right hand side pure function of x only. When you divide by this, you will get this y raised to power minus n dy by dx plus this is y by y raised power n. P is only q now. This gives you y raised power minus n dy by dx plus y raised power y1 minus n. P is equal to q. Now you have come to know where does this y raised power 1 by n comes, which we just stated there. We can reduce this Bernoulli's differential equation to the standard form of the linear differential equation by the transformation z is equal to y raised power 1 by n. I am just telling you, explaining you how this, where from this y raised power 1 by n comes. It has come here. Now this is your y raised power n. If I make the substitution here now, if I put the transformation z is equal to y raised power 1 minus n and differentiate both sides with respect to x, because y is a function of x. It is dz by dx, it is down, it is 1 minus n, this is y raised power minus n dy by dx. This gives you dy by dx. That means I can write that my y raised power n dy by dx is now y raised power minus n, y raised power minus n dy by dx is 1 upon 1 minus n dz by dx. So I have got this directly by putting this equal to new variable z or theta, whatever you put. You have got y raised power n dy by dx is equal to dz by dx. That means equation gets transformed now. In terms of the y, in place of the y dependent variable, my z is now dependent variable, x is independent variable. When I use this in second, this transformation, using this value in second, what I get when I use it in second? Well, when I use it in second, this is your instead of this I will write it now. It is 1 by 1 minus n dz by dx, and we have put this z as it is plus z what was your this with z, just I will find this was your dy by dx plus py is q y raised power n. Yes, when you divide it, y raised power n plus, yes, it is your p, it is your zp, z into p, z into p, it was your z into p is equal to q. What now we will get dz by dx will be your, yes, plus, this is plus p times 1 minus n, p times 1 minus n is equal to q times 1 minus n, multiplying third by 1 minus n. Now it is a linear differential equation, z here, linear differential equation. Which form? dz by dx plus, say it is p dash z is equal to q dash. What is p dash and q dash? These are functions of x. This is a function of x. Because our p is a function of x, it remains function of x with constant 1 minus n, and it is also function of x. So what is your integrating factor here? Your integrating factor will be now integral of 1 minus n p dx. That is, integrating factor is p raised power 1 minus n integral of p dx. Now you find it and use there. You will write then solution is what? Z times integrating factor, it is solution. is equal to integral of your q dash. Q dash is your this. It is q dash. What is your q dash? It is this. Q dash into dx again plus c. Then this differential equation gets now transformed to the previous one by this suitable substitution. This is how we reduce the Bernoulli's differential equation. When we have a Bernoulli's differential equation, we can reduce this Bernoulli's differential equation to again this differential equation of the standard form. Let us have some applications. I have given you the method of solution. We have now some applications of this. Now we have some applications. I have mentioned there some application. I will write again here. Suppose I have first application, solve the differential equation. I have to solve the differential equation. dy by dx is equal to x cube y cube minus xy. You have dy by dx. You just look, y is also existing in linear form. The linear power of y, I will transpose to this side. It is dy by dx plus xy is equal to x cube y cube. This is your differential equation. It is of course Bernoulli's type. You see, your differential equation is actually dy by dx plus py is equal to q, where p and q, these should be constants or functions of x. These should be either constants or functions of x. It is your dy by dx. Y is linear. Okay, we need it on right side. I need pure function of x as per the standard form of the linear differential equation. So what is the obstacle that I have to remove here? It is obviously this x cube, y cube. On right side you should not have the y cube, because presence of y cube makes this differential equation not, where we say it is not linear differential equation due to the presence of y cube. Now how I remove this y cube? Very simple, as we did in the dy by dx plus py is equal to q into y raised power n. What we did there, we divided by y raised power n. On right hand side we have removed y raised power n. Similarly here I will remove it. I will go this way. I will write divide both sides by y cube. When I divide by y cube, it will be your 1 by y cube. It is your dy by dx. It is plus xy by y cube, and it is equal to x cube. You see, it is y raised power minus 3. It is your dy by dx. It is your this by this is y raised power minus 2. It is x is equal to x cube. Okay? X cube. This is your equation number 2. So we have divided by y cube. This has got transformed into this. Let me now put here y raised power minus 2 is equal to transform no variables are. Differentiate this. What is this? Minus 2. It is y raised power minus 3. dy by dx is dz upon dx. But I want to find out this. You see, you get it here. So I am getting y raised power minus 3. dy by dx is equal to what? It is minus 1 by 2. Minus 1 by 2. Minus 1 by 2 into dz by dx. So I have got this y raised power minus 3 dy by dx is minus 1 by 2 dz by dx. You see, second equation reduces to now equation number 2 is, equation number 2 implies me y cube minus dy by dx. It is your minus 1 by 2 dz by dx, then plus y raised power minus 2, you have put it z, x is equal to x cube. Now I want to get rid of this, multiply both sides by minus 2. It is z by dx, dz by dx plus minus 2 x z is minus 2x cube. When you multiply by minus 2, it is plus, it is minus 2x here, minus 2x. Now this is your standard form of the linear differential equation. But you have to remember your substitution, y raised power minus 2 is z, because we need it at the end. We need it at the end. I will write here our substitution here, z is y raised power minus 2. We will need it later on. So rest I will rub here, rest I don't need. Now you see, this is now a standard form of the linear differential equation. Which form it is? It is this form. dy by dx plus p of z, dz by dx, sorry, dz by dx. It is dz by dx plus p of z is equal to q, where p and q are functions of x. Dependent variable is your z. It is independent variable is x, and p and q should be functions of x or constant. This is your function of x, this is your function of x, this is your p, this is your q. So it is the linear differential equation of standard form. So what will be your integrating factor? So integrating factor in this case is, your integrating factor is, it is e raised to power integral of p dx. It is equal to e raised power integral of what is p? E raised power minus 2x dx. This is your e. So what is integrating factor? Integrating factor is e raised to power minus 2 integral of x dx. That gives you e raised power minus 2 integral of x square with respect to x, with respect to x, is x square by 2. So this gives me integrating factor e raised power minus x square. Okay? Well, so according to this, what is the solution? So solution of third equation is, how you write solution? A dependent variable, that is z. Then it is integrating factor, integral of q. What is your q? It is this. It is integrating factor. First we write integrating factor, then q minus 2x cube with respect to dx plus. It is the solution of a simplified. Z integrating factor e raised power minus x square, then integral of e raised power minus x square. It is minus 2x cube dx plus c. That gives you, let me put the value to this z. What is the value of z? It is y raised power minus 2. I will write it. Y raised power minus 2 e raised power minus x square is equal to minus 2 integral of, it is x cube e raised power minus x square dx plus c. Now I have to finally solve this integral. Now I have to solve the integral. Solve now. Y raised power minus 2, x raised power minus, x raised power, e raised power minus x square. It is e raised to power minus x square is equal to minus 2 integral of x cube e raised power minus x square dx plus c. Now how should I go? This integral seems to be typical, but it is not typical. We can do it different ways. The best way will be to go by substitution. We can solve it by substitution method. How do we go by substitution? You see, if we put, we write this way. This is your minus 2. Right there, x square e raised power minus x square x dx. Why I am doing this? If I put x square, I won't get, there is, if I put x square, this x cube, no doubt this will be 3x square. 3x square. But that will not solve my problem. I have separated this because here I have x square. I am also writing this x square e raised power minus x square dx. Why so? Because derivative of x square is 2x dx. So in the derivative of x square, x gets involved. Therefore, the suitable substitution is here put x square is equal to say t. What is this? It is 2x dx is equal to dt. So I have got x dx is equal to 1 by 2 dt. It would otherwise become difficult if I make the substitution there x cube or I make some other substitution. So better is to separate x cube, write it x square. That because we know that in the derivative of x square I can get x dx. So I am going this way. This is your y raised power minus 2 e raised power minus x square is minus 2 integral of your x square is now t. It is t. E raised power minus, it is e raised power minus t. Your x dx is what? 1 by 2 dt plus c. You see how you reduce this now. 1 by 2 dt. This is what y raised power minus 2 e raised power minus x square is 2 rows. It is minus integral of t e raised power minus t dt plus c. Now how you integrate such integrals? Product of two functions. We take one function u, second v. Now it is better, it is derivative reduces to constant. It is better to take that function u whose successive differentiation reduces to constant. Or you can go by Euler u. I can take u is equal to t, v is equal to e raised power minus t, and integrate by parts. I am integrating by parts. So this is y raised power minus 2 e raised power minus x square minus u as it is. U. What is your u? T. Integral of e raised power minus t. It is e raised power minus t by minus 1. Minus whole integral. Derivative of t, it is 1. Then e raised power minus t by minus 1. dt plus c. Then this is your y raised power minus 2 x raised power x minus e raised power minus x square. This is your I will write minus outside. This is your minus t e raised power minus t. This will be your minus plus integral of e raised power minus t dt plus c. When this gives you e raised power minus x square, you can write y square is equal to minus times, it is minus t e raised power minus t, integral of e raised power minus t, it is minus e raised power minus t, you know, then plus c. Because integral of e raised power minus t is e raised power minus t by minus 1. This is e raised power minus x square by y square is equal to, you can take e raised power minus t common, minus inside this plus e raised power minus t into e plus 1 plus c. You can write the solution of this problem as, solution is now e raised power minus x square is equal to t plus 1 e raised power minus t plus c into y square. You can write the solution in this way also. Or e raised power minus x square is, this is x square plus 1 e raised power minus x square plus c y square. You can further simplify this. E raised power minus x square, e raised power minus x square common. This is x square plus 1. This is plus c e raised power plus x square. Because when we take e raised power minus x square common, it will be x square plus 1 c by e raised power minus. I have taken in the numerator. It is your plus. It is your plus this x square. It is y square. So that this e raised power minus x square, e raised power minus x is goes. So I can write solution is 1 into simplified form. It is x square plus 1 plus c is for x square integers. You can write the solution this in simplified form, or you can stop the solution here, right here where our x square is t. This is how to solve this Bernoulli's differential equation. I had written here some more. I would just share with you some more solutions. So I will do it next because it is at this time raining in our Kashmir, and there is a dim light, very dim light, and it becomes very difficult to go ahead. Let us meet next. I wish you all the best, and you will do the questions on this Bernoulli's differential equation. We will solve more and more questions on this. I will share some more problems on Bernoulli's differential equation. Thank you.